All right. Thank you very much. It's a real pleasure to be here. All right, so I'll be presenting some joint work with Sergei Strechuk from University of Cambridge. And I guess that the main objective of this talk is to highlight that quantum capacities, at least some of them, are multiletter. They have to be regularized, and this is in stark contrast with the classical case. So I will motivate my talk with some stories. So I met little Alice and little Bob this morning, and they wanted to communicate privately, even in the presence of their teacher, Eric. So I proposed them I would give them two channels, quantum channel blue and quantum channel red. But I allowed them to choose just one channel for their purpose. So which channel should they choose? I guess if they are going to communicate lots of data, maybe the answer to this question is very easy. They should choose the channel that has the largest private capacity. Easy, right? Or maybe not so easy. So we will leave Alice and Bob right now. They will think about some way of choosing the quantum channel. And we will go back to them at the end of the talk, and we will see what are the consequences of the way that they have for choosing the quantum channel. So the structure for the rest of the talk is as follows. First, I will introduce quantum channels, private capacity, and I will state our main result. This statement relies in some very concrete channel construction that I will present in the next section. And then I will proceed to sketch how one would prove that this construction has a very funny behavior. Then at the end of the talk, we will go back to Alice and Bob. We will see how they would choose their channel, and we will see what consequences that choice has. Okay, so quantum channels. Quantum channels are basically maps that take quantum states to quantum states, even if they are part of a larger system. So I will indicate with a superscript the origin of the channel and the output of the channel. So this channel goes from A prime to B. And we can always embed a quantum channel into an isometry. The isometry goes from the input of the channel A prime to the output B and some external system E. We recover the output of the channel if we trace out this system E, that stands for environment or eavesdropper, and we obtain what we call the complementary channel if we trace out the output of the channel. So very informally, the definition of private capacity is the maximum rate at which we can communicate arbitrarily faithful, but at the same time we can keep the environment arbitrarily ignorant. This is, of course, just one possible task for quantum channels. We could think of other tasks. For instance, we can think about communicating classical information through the channel. Of course, in this case, we make no requirement in what happens with the environment, so naturally this is going to be an upper bound on the private capacity, and I will use this relation a little in the following. All right, so the previous was some operational definition. How can we characterize the private capacity of a channel? First, we introduce the private information of a channel. This is going to be the maximum over all classical quantum states, classical in some external system X and quantum in the input of the channel A prime, of the difference between the mutual information between X and the output of the channel B minus the mutual information of X with the environment. Then we can define the n-use private information of the channel, which is nothing more than the private information of n uses of the channel divided or regularized by the number of uses n. And finally, we obtain the private capacity of the channel, which is the lim when n goes to infinity of the n-use private information. As promised, this is a multi-letter formula, regularized formula. But in some cases, we are lucky. So for some families of channels, we have a single letter formula. For instance, if the channel is degradable, that means that there exists some map T that takes the output to the environment, and in a couple of other cases, such as conjugate degradable of less noisy channels, we have a single letter formula. And also, the complementary of these channels have single letter formula. So an anti-degradable channel would be a channel where the environment, there exists a map that takes the environment to the output of the channel, and in this case, we can see that the environment has a certain advantage over the output, so basically these channels have zero capacity. For An arbitrary channel, in general, we do not know if it has a single letter formula or multi-letter, but we do know that some channels need the multi-letter formula. This was first pointed out by Smith and Nolan in 2008, and they showed that some channels have private capacity that is strictly larger than private information. And these channels were not very strange channels, where the channel that arises in BB84, and it was the depolarizing channel. Okay, but with this evidence, we could maybe still hope that there are some n such that the n used private information equals the private capacity. That is, superadditivity can have some limit. But our main result is that this is not the case. So for any n, we can find some channel n such that the n used private information is strictly smaller than the private capacity. That is, superadditivity does not have a limit. So I said before that this result relies in some very concrete channel construction. So let's see how it works. So one of the ingredients of this construction is a direct sum channel. We call them switch channels. They were introduced by Fukuda and Wolf in 2007, and then they are very simple machines. They have two inputs, a control input and a data input. The control input gets measured in the computational basis, and depending on the output, a different component channel is applied. Why do we like these channels? Because their private information can be analyzed a little bit more easily than in the general case. In particular, their private information is going to be given by the maximum of the private information of the component channels. So our construction is going to be a switch channel with two concrete component channels. One of them is an erasure channel, a quantum erasure channel. It takes the input to the output with probability 1 minus p, and with probability p, it outputs some flag. If p is smaller than 1/2, the channel is degradable. If the p is equal or greater than 1/2, the channel is anti-degradable and has zero private capacity. This is the regime in which we are going to be interested. And a very useful lemma for these channels is that the private information of any channel used together with an erasure channel is upper bounded by the classical capacity of the channel plus the classical capacity of the erasure channel. The second component is a rocket channel. So rocket channels were introduced by Smith and Smolin in 2009. They also have two input registers, the same dimension d, and every one of the registers gets applied a random unitary. These random unitaries are not known to the encoder, to Alice. And we can see that if Alice knew the second one, and after applying the unitaries, they are jointly dephased. The first register goes to the output of the channel, the second register goes to the environment. All right. So if Alice knew the second unitary, then she could prepare some input that somehow compensates for the dephasing, and the channel would have would behave like the identity on the first register. If at least she knew U, the first one, then she could prepare some inputs in the dephasing basis, and the channel would have full classical capacity. But she does not know any of both. So basically, it turns out that these channels, no matter what the input dimension, have a classical capacity which is upper bounded by 2, and in consequence also a private capacity which is upper bounded by 2. So our construction is, as I said before, a switch channel that allows us to choose between n rocket channels and an erasure channel. So why do we want to match erasure channels with rocket channels? So the reason is because separately they have very little capacity, but together they can have large capacity. So the idea is that if we put a maximal entangled state between system A2 and system A3 over an erasure channel with probability 1/2, which is a channel with zero capacity, then if the channel erases, basically nothing happens. But if the channel does not erase, then Bob can undo all the rocket channel, and the channel is going to behave like an identity on the first system. So we see that the private information of the joint channel is lower bounded by 1/2 of log d, where d is the dimension of the system A1. Very good. So now we can go to a sketch of the proof that this channel has a very particular behavior in terms of private information. So we are using these switch channels that allows us to choose between many copies of the rocket channel and a d-dimension erasure channel. So what we need is some not very bad bounds for the k used private information. So for an upper bound, we just need to upper bound all choices of component channels, And for the achievable part, for the lower bound, we are going to need a concrete protocol that achieves some concrete private information. What we are going to do is to choose the rocket channel for the first use, and for the remaining k-1 uses, we are going to choose the erasure channel. So this basically will unlock one rocket channel per channel use. And finally, we need to prove that we are going to prove that for all I smaller than n, the I use private information is upper bounded by some U that is strictly upper bounded by some Ln that acts as a lower bound on the n use private information. And this implies the result that we want. So the converse goes, as I said, we upper bound over all choices of component channels. If we choose only rocket channels, we have that the classical capacity is upper bounded by 2. We have Kn, so 2Kn. Here we can use the lemma that I said before. And if we use all erasure channels, this is in the anti-degradable regime, so this is going to be upper bounded by 0. For the achievability part, we can compute the concrete private information in the same way that we did in the example before, and we get this number here. So basically we get some upper and some lower bound. We have some degrees of freedom in terms of the input dimension and the probability of the erasure channel. There are some algebra, it's not very complicated, but also not very illustrative, and we get the result that we wanted. For all n, there exists some channel n, such that the n-use private information is strictly smaller than the private capacity. Okay, so we gave Alice and Bob 10 minutes, and this is the very sensible protocol they've come up with. They are going to fix n, the number of uses of the channel. Then they are going to compute the private information of channel blue and the n-use private information of channel red. This is, of course, fiction. As far as I know, there's no way of computing the n-use private information. But let's suppose that they can. Then what they are going to do is they are going to choose the channel with the largest n-use private information. But I chose two very particular channels. So for the blue channel, I choose the channel that comes out from our construction. So that's a channel that has some upper bound U on the private information that is strictly smaller than L that acts as a lower bound on the private capacity. And for the red channel, I'm going to use the erasure channel that has exactly private capacity U plus L over 2. So now Alice and Bob implement their protocol. So they find out the private information of the blue channel, that is some number which is upper bounded by U, and then they find the n-use private information of the red channel, which has private information U plus L over 2. So they choose the red channel. So they've done some Herculean effort to compute the n-use private information of channel blue and channel red, and still they're going to choose the worst of the two channels. So very bad for Alice and Bob. All right, so some final discussion. So there's this superadditivity, so now what? So it would be interesting to characterize additivity. So we have some families of channels that have additive behavior, that they are single letter, are there other families? I don't know. Another very interesting line would be to bound the effect of superadditivity. So by this I mean to establish some bound in the difference between the capacity and the n-use private information. So there are some very recent results that bound the difference between the capacity and the single-use private information. As far as I know, they cannot be generalized, but it would be, of course, very nice to have some upper bound as a function of the number of uses n, and even nicer if that bound were to zero with the number of uses, but that might even be false, so who knows. And I've been talking about, all through this talk, about a concrete characterization of private capacity in terms of regularization of private information. But is it possible that there are some single letter characterization of private capacity? I don't think so, but it's not completely impossible. So to illustrate that, the classical capacity of a classical channel is given by this maximization of the mutual information over all input probability distributions. So very nice, but imagine an alternative world with where there was no closed Shannon, and some guy would have proposed this other entropy quantity, the harebrained information. This is the maximum of the entropy minus twice the conditional entropy of x given y. So this is, of course, upper bounded by the capacity of the channel, and for most channels is strictly upper bounded by this capacity. But if we take the regularization of this harebrained information, we obtain the classical capacity. So then the question is private information some harebrained quantity? So I don't think so, but it's a possibility. So For the moment, we will let Alice and Bob to continue their search for a good way of deciding which channel they should choose, and I will answer your questions. Thank you very much.
Hi, David.
Hi.
Thanks for the talk. I just have one question. So, in your example, you were talking about Alice and Bob having n uses of the channel. But in this case, we know that it's not really this regularization that plays a significant role. It's you actually have to, you can't just take this asymptotic
Yes, so maybe I was not precise. So that, in this little story, Alice and Bob want to use indefinitely the channel, but they are going to compute the n-use private information. So of course that does not correspond with using the channel n times. It's a different picture. I agree. Maybe I was not clear.
Okay, yes.
Okay, I think there are no other questions. Please move to the last talk of this session. Thank you. Thank you again.